wanted to thank Dr. Tao as well as Carol McFarland for organizing everything here and inviting me. So it's a pleasure to be here this morning. And I also wanted to give some credit to one of my co-authors here, Chu-Ping Peng. She was a doctorate student candidate at Washington State University. Ellen, can you kind of show yourself? Where are you? There she is back there. So if you have any questions about this presentation, ask Ellen. She put together lots of the data. And I also saw Dr. Tabitha Brown. Oh, she's here. She also contributed to some of this as well. So she's up here too. I love this shot. And this is a soil profile from the Cook Agronomy Farm, so just outside of town here. And the title, soil carbon is not soil carbon is not soil carbon. I've been studying this for about 20 years now. And the purpose of that is just to say, oh my gosh, there's a lot of different kinds of carbon in the soil. And even looking at this particular soil, you can see the dark layer up here. This is definitely enriched in soil organic matter, right? That's that dark color that we see. This is also enriched in carbon. It's just a different kind of carbon. It's inorganic carbon. So it's calcium carbonate in this case. That's that whitish color that you see here. So we have two enriched profiles here from the standpoint of carbon. And this, of course, starts to lead to questions about, well, how do we measure things? What are we measuring? Where will we measure it? At what time will we measure things? And then how will we interpret all those measurements as well? And of course, that gets into complexities in terms of, well, what's the purpose of your measurement? What are you trying to figure out from the standpoint of carbon? But it's good to remember that there's both organic and inorganic carbon, first of all, in our soils. And in some cases, it could be quite prevalent. Even here in the Palouse, this is less common to find, but it's in eroded topsoil or in eroded areas in the field. You'll find this type of soil profile. In this case, this shows the legacy of a lot of impacts of management in the past. There used to be another horizon between this horizon and this horizon that basically has disappeared because of tillage and erosion processes that have basically exported soil off the top here. Then we've dug into this subsoil like this. It's interesting, this is kind of a self-liming process from the standpoint of mow-bore plowing basically and erosion processes and incorporating then some of this inorganic carbon. It's basically lime material right into the topsoil here. And it's not that I'm recommending that from a liming program, but it's definitely where we find some of our higher pHs up still towards neutral in the same field where we might find something that's quite acidic. And so that's a story of carbon that's undergoing in our soils from the standpoint of tillage effects over time. And we're going to talk about that a little bit. It's definitely, kind of the star of the show from the standpoint of productivity, et cetera. And we know that organic matter is kind of like mother's milk, to soil scientists in particular and to farmers. So where do we come from in terms of soil organic matter trends? Some of this, you can say that we started off here at around 6% or so soil organic matter, and then we slowly declined over time. Part of our challenge is to actually set thresholds in terms of, well, how much is enough? How much actually satisfies some of the expectations we have from our soil in terms of yield and other functions that organic matter have in terms of nutrient release and all those other good things, feeding the microbes, et cetera. And so part of the question is, well, what's the target level here? When should we be starting to get concerned about where we are at? I'll talk a little bit about that, and why did I pick 3% in this case? And that's a good question. We also have impacts then of various kinds of practices that can be engaged in. We call this, a fancy word for this is adaptive capacity. What kinds of options do you have from the standpoint of farming to actually impact what this curve looks like, and to either put it in a different direction or to continue to go downward from the standpoint of what's going on with soil organic matter. And in this case, this is some summary from Dr. Brown and myself in terms of looking at the literature and saying, oh my gosh, well, if we get into a mixed perennial annual, then we can probably increase at a rate faster than we can with almost anything else. Here's no-till here, kind of coming back a little bit slower in terms of its adaptive capacity and capability to kind of recapture some of the organic matter in the soil itself. And this is the top 15 centimeters, I'll just emphasize that. And then fallow, anytime we have fallow, it's real difficult to maintain soil organic matter levels. Basically, we're not providing the carbon inputs, right, that are needed to actually sustain the soil from the standpoint of soil organic matter levels. So here's some really old data. It says Jennings et al. 1990, but I think this data actually is derived from the 60s. You'll notice that these kilograms per hectare, okay, 6,000 is about 100 bushel wheat. You can see that these levels are fairly low, and I suspect this relationship is a little bit different now than it was back then. And part of our current research is to actually recreate this particular graph, because I think it's a pretty interesting one. This has topsoil depth in terms of centimeters, remembering 30 centimeters, about a foot or so. This is 2 feet. And then here's versus yield, but then it has it at different soil organic matter levels. And you can see that as we get upwards of 3%, that we're starting to level off in terms of yield impacts. And this is, again, old data. I have no clue what this data might look like for our much higher producing systems that we have today, but that's something that I'd be really interested about. But this starts to get at that question is, how much is enough? What's the target level that we're looking for? That's one of those challenges. So a little bit in terms of, people talk about resilience a lot and the necessary for our crops to increase their resilience. There is resilience theory, ecological resilience theory, that actually defines some attributes that are important to think about. And I think they're particularly important for looking at soil health, because we can combine soil health concepts with resilience theory to actually start to define what some of these thresholds are. Well, what is healthy? Whoops, sorry. And I got ahead. What is healthy? What's the key property indicator that becomes healthy? What's the thresholds that we're looking for? They can be lower or upper thresholds. What's the current state terms in relation to those? Where are we in relation to those thresholds that we're trying to look at and define? That's kind of precariousness. And then the monitor the rate of change, that's kind of the resistance. The resistance can be, okay, how slowly or rapidly is that property changing and approaching a threshold? How, either towards it or away from it. Both of those are important characteristics to think about in terms of soil health. And then coming back to this concept of adaptive capacity, what kinds of management impacts do we have on health and resilience? And can we develop systems that improve health? What do they look like? And so those are the options basically available. So I'm going to tell you about the Cook Agronomy Farm, established back in 1998. It was established as a location where we wanted to go more field scale. The original farm was this 92-acre piece right here, it's just outside of town. We wanted to look at spatial variability, but we also wanted to look at temporal variability. How do things change over time? And going back to that resilience theory, that's basically looking at, okay, how does management impact things over time? And many things take a while, right, to change. It doesn't happen in a year or two often, particularly with soil organic matter. It's decades that you can have an impact in terms of building or depleting some of those kinds of levels. And so we also, back in 2012, we were actually designated nationally as a USDA long-term agroecosystem research site. And so the Cook Farm is now part of this national effort. So you'll see that symbol. That's the symbol for this USDA long-term agroecosystem research. I still can't say it. In terms of LTAR, I say. That rolls off the tongue a little bit better. So LTAR site. And so that basically is putting long-term research into our research portfolio. And we feel really fortunate at Washington State University that we have this with USDA in terms of looking at some of these kinds of management impacts on soil properties and other things. So we wanted to understand the variability out here. A couple of years ago, we combined it with the watershed right across the road, and this has been managed with reduced till. So we come in, we still use a no-till drill under low residue crop conditions like winter wheat following our garbs, but we'll come in after the winter wheat residue and basically use a chisel plow. It's a disc ripper, and then plant our spring wheat after that. So that's one difference in terms, but this has been managed then, this piece over here on the west side of the road for the same 20 years in that type of reduced tillage system, whereas this part of road over this portion of the field has all been direct seed of some sort over time since '98. So here's what soil organic matter looks like. These were samples that were taken back in 2017, and they're in 30 locations on each side. You can see that we're calling this the aspirational in terms of direct seed, and also we're supplying nutrients from the standpoint of precision ag. But you can see that organic matter in the top 10 centimeters, top 4 inches, is basically fairly good. It's getting up above that 3% level. And I say, but you can see that different portions of the field, these are contour lines. This is an eroded knob up here. You kind of wonder about those locations in the field and whether or not they can respond to direct seed over time, because they may not have as much carbon inputs in terms of their yields to actually provide the inputs required to actually increase levels or increase them as rapidly. And so you can see though that this contrasts quite differently than you can see over here in our reduced till situation. We still see active erosion on this site in terms of surface runoff and sediment deposition down the field and then also alongside the road. Here we rarely see very much runoff at all. So we basically curtailed the erosion down to almost nothing from the standpoint of water erosion on this site. Oh, I put this in there. Here's the Haney Soil Health Index. And the reason I put this in there is there's been a lot of interest in trying to assess the active carbon, the active organic matter that's here, that in the soil that provides some of this food for microorganisms, that contributes to nutrient cycling, et cetera. And so the Haney test is one of those tests that starts to try to look at that from the standpoint of different measures. And so it's interesting to see in this case, it has this C-min up here basically is the Salvita test. It's the release of carbon dioxide in a respiration type of test. You bring the sample in, dry it down, expose it to water, then the microbes get busy. They basically feed on the organic materials that are easy to get to in terms of food. They respire, just like you and I do. They release the carbon dioxide, and that's what's measured, okay? So this is over a 24-hour period. You measure that carbon dioxide, and that's a measure then of how active, basically, the microbes have been for that particular test. And so that's also in this test is water extractable organic carbon. So here's another measure that's trying to get at this active organic matter as well. This is basically the stuff that's soluble, okay? Those materials are thought to be more, there's of course discussion about that, and I'm sure some of those water-soluble organics aren't actually that readily available to microbes, but this is another measure that's trying to get at this active organic matter. The permanganate oxidizable carbon is another measure that's also trying to get at this active level, and some labs are starting to provide that type of measure as well. So there's multiple measurements now in terms of tests that are kind of targeting different kinds of organic matter in the soil that then can be interpreted in terms of how your management is impacting those kinds of tests. The Haney test was one of those. We haven't found it to be all that useful, though I'll say that the Salvita test has been, I think, is an interesting one. We are seeing some kinds of differences with that. The issue here with just 24 hours of this test tends to be quite variable. And so the variation that we see in that test starts to basically detract from its usefulness. And what we find is that we need a longer period in terms of incubation in order to actually see the expression of differences in management. Okay, so in other words, if we keep this respiration going in the test for a number of days and sometimes weeks, then we can start to see the accumulation of that respiration actually separate management effects over time. So this 24-hour period it's convenient from a laboratory perspective, I know, but from the standpoint of actually being useful to separate differences in management, it's not been as useful for us for that purpose. So here's the soil health test, the Henny test, and basically here's both sides of the field again, top 10 centimeters, and you can see there's, well, we didn't actually see where this test actually provided a way to look at differences in these fields. Some variability, you notice, across it, but overall, not much difference here on average across these fields. And here's the CO2 burst, and again, not a lot. This is the top 4 inches, and again, this is where we saw the differences in soil organic matter here, but in this case, in terms of the CO2 burst for 24 hours, again, we're not seeing a whole heck of a lot of difference here in terms of, again, variability out there, and that's important to recognize because that gets back to, okay, where the heck do we sample in this field to get a representative sample? So that's always an issue that comes up. But again, this one not showing us a whole lot, and again, and here's for and here's for the next 10 inches, or 10 inches, 4 inches. So this is from 10 to 20 centimeters. And you can see that this is where acidification, and our acidification layer is right in that same area. And you can see that has had a bad impact in terms of the CO2 burst. So that acidification process, that stratification of acidity is impacting our microbial activity. And you can see it expressed here in this map. Again, how much is enough? What's the thresholds and values that we're trying to shoot for? Good question. This is just a relationship between that CO2 burst in the Salvita test and then the Haney soil health test score. And basically it just says that much of the differences in this health score are being driven by this CO2 burst rather than the water extractable organic carbon and the other factors that were in that equation. So that kind of just emphasizes, this is what's driving differences across our different depths, et cetera. But again, how sensitive this? What are the values we're trying to shoot for? Good question. That's the Haney test across all kinds of different management. It was kind of disappointing from that perspective because it just kind of showed not very much discrimination between very distinct different kinds of management. In other words, long-term moldboard plowing 30 years versus no-till for, these are the long-term kinds of studies that are out there. And so this then doesn't provide a useful measure in terms of a metric there where we want to actually assess soil health. For us, it might work in other areas, but for us, this just wasn't something that was working out very well. Total PLFA, that's the phospholipid fatty acid. So this is actually a measure of total soil microbial activity, and so it's highly correlated with this. So this is a measure that's, again, trying to look at that more active piece of the soil in terms of organisms. And you can see that we're a little higher, with that test in terms of what we're seeing over at Cook Agronomy. Again, spatial variability. Again, questions can be made about, well, what is enough? Is this high, really? Can it be higher? Is lower okay? So those are questions you could still ask, but you can see quite a bit of variability again, and there's probably some interesting kinds of relationships that we could start to derive from this particular type of test as well. And this is one that Dr. Jeremy Hansen might be talking about a little bit after me, but this is another test that I'm kind of excited about from the standpoint of how do we assess what's going on in the soil and the kinds of microbial populations that are there. And I put this slide in here just because, well, my gosh, it's not just management, not just us folks. As we look at the climate that we have, and in this case, this is the mean annual temperature basically divided by the mean annual precipitation. Okay, so that's the driver. So if you just look at that ratio, it's called the climate index, and it's highly, in this case, related to how much soil organic matter we have. So this is from the dry locations, right onto the wetter locations. This is starting to to look to assess then, and this is not just used, this is for Palouse or for our dryland region, but this is a type of measurement that's been used for the Midwest and elsewhere to kind of just look at, well, what's the climate effect in terms of soil organic matter? And you can see the management is kind of scattered around that line, but this is the impact then of just climate across our area in terms of organic matter levels. And this comes back to how much water is available to basically grow things that produce carbon and have the capacity to build soil organic matter in the soil itself. So here we are in the Palouse. Well, lots of things going on. It's kind of a real researcher's dream in terms of the variability that's out there and trying to figure it out. It could be a nightmare for others. This is an interesting study by Ann Rodman. She was a grad student back in the 1980s, and she went out to one of the native sites that we have just south of town here and did a kind of across the fence row comparison of the native site versus a field that had been in ag over the last 100+ years. And it's interesting and she looked at it in terms of different landscape positions. Here's a south back slope, a summit position, a north side, that's convex versus a north concave, and then a foot slope position, so down in the lower portions of the field. And you can see, first of all, that, okay, on those south sides and upward positions, there just wasn't as much organic matter to begin with. So here's soil organic matter. In this case, it's megagrams per hectare. It's not percentages. This is actually amounts that are there, okay? So this is another measure of basically content versus concentration. But you'll notice that the red is the native prairie. This is the sum over in this case, 125 centimeters. So that's, what is that? That's close to 4 feet or so. So that's assessing things on a pretty good depth in terms of the organic matter. And you can see that the impacts of 100 years of cultivation, 50 versus 40 in terms of microgram of carbon. Here at the summit position, the most impacts, and you can consider that erosion has probably played a key role here, and you'll see that there was a lot more carbon here to begin with, and then we lost a lot in that particular position. And as you move to the north side and the north concave, you start to see things that kind of shift around a little bit, still losing quite a bit of carbon in terms of those comparisons here throughout the soil profile. But as you move to this concave position, this is where we can have more deposition in terms of soil in the landscape. We're finding that, oh my gosh, here in the subsoil anyway, we're starting to get more carbon expressed or measured in the subsoil itself, and in some cases starting to match or be a little bit more so than the native conditions. And then when we look at the foot slope position, my gosh, look at this. We actually have much more carbon in the conventional system stored basically than we have in the native condition. And why is that? Of course, we had lots of deposition from erosion, right? That's carried carbon down. Erosion is a selective process. It's transporting, organic materials from the surface down the slope. It's depositing in those lower slope positions, and then that subsequently gets buried, right, by subsequent kinds of erosion activities. It can actually result then in buried topsoil conditions, and that's what we're seeing here. This probably at one time was not only near the surface, but then also got contributed to organic matter, and then tillage, et cetera, has buried it, and further deposition on top of that has basically buried some of these stores of carbon. So this becomes an interesting question in terms of, well, what happens to that carbon when we start to go to no-till? Because we've got very different kinds of situations in any given field around here where we have different levels of carbon to begin with. And does going to, for example, to no-till start to either support or not support those levels of carbon that are there? So I put together this little simple hypothesis probably 10 years ago now. I think I can almost answer it at this point. But this just takes, so here's the native prairie. Here we are with conventional tillage. And we have some erosion degraded situations in the field where carbon levels have actually increased some. And then we have other locations where it's degraded. And here, maybe the overall impact is a reduction in organic carbon over time. But now we have no-till, and what's going to happen? Are some locations going to increase where others decrease. And you might say that, oh my gosh, the erosion degraded, how do we maintain those levels? Because the carbon inputs that we have are not substantial enough to actually maintain the levels that are there. And so if you have higher amounts of organic matter in the soil, it's going to take more organic inputs each year in order to maintain those levels. Okay, and so that becomes a question. And there's other portions of the field, hopefully, where we're going to, if we still have the productive capacity, that's the other thing, what's the capacity of a particular location to actually produce crops and produce carbon that can be, in turn, then put back into the soil to build soil organic matter. So, question. So, Cook Farm is kind of known for going to town in terms of having georeferenced locations, and make the point that georeferenced locations are extremely critical to establish in terms of setting up long-term kinds of monitoring of a particular field. The question is, well, how many of these locations do you need? And we have 369 that we've located on this 92-acre field. That's basically was determined by how many cores could we take. You know, it was more along those lines. And these are some examples then of the kinds of cores down to 5 feet that we took. And you notice in this particular field, this black area here, that's very low topsoil levels. And then you can see some where the darkness continues for quite a while. There's some interruptions there that are interesting. And then you can see, though, these are examples of different profiles and the darkness indicating variation across this particular field and how much carbon is actually there. And that was the purpose of putting in so many georeferenced locations. We had no idea what that might look like over this particular field, and we just thought more was better until we couldn't do anymore. So lots of excitement in terms of operations of Giddings probes and GPS at the time, and we continued then with sampling, baseline sampling to begin with back in 98 and 99, and then follow-up sampling in 2008 and 2015 to kind of see, well, what kinds of changes are we going to see in carbon levels over that time period after we had converted that kind of reduced till scenario to continuous direct seed. So I'm going to go through different layers again. This is 0 to 10 centimeters, so that top 4 inches type of thing. This is where we would expect to see the biggest change in terms of conversion from a tillage regime that basically incorporated the residues to one where much of those residues returned to the surface. We get the stratification, we get a buildup of carbon at the surface itself, and that's what we saw during the first 10, 11 years here. And this is just a map of that. I've given the ranges here, and then the mean and the standard deviation. So here's the range that's kind of fun to look at, 13 to 36 megagrams of carbon per hectare. I will say that in terms of research and in terms of issues like carbon sequestration, actually measuring the carbon is important rather than the organic matter itself. Organic matter ranges in terms of its carbon percentage, 50 to 58% or so, give or take. And measuring the carbon itself is done through dry combustion. Basically, we heat up a sample to a lot of 1,000 degrees or so, and it basically burns all the carbon off. And that carbon includes not just the organic carbon, but the inorganic carbon. So if we want to actually get at the organic levels, we have to first add an acid, basically, that blows off the CO2 that's in the inorganic form to just measure, and then just measure that sample again to get at the organic carbon that's there. So these data all express the organic carbon that's there, not the inorganic carbon. That's a whole other story. We've been acidifying our soil, so no doubt the inorganic fraction has been declining over time. That's also should be part of the equation in terms of looking at carbon sequestration, particularly from a greenhouse perspective, and how much CO2 basically is being evolved from these samples and how much carbon is left in the soil itself. But here we can see the range in 98, 0 to 10 centimeters, on average 26 megagrams per hectare, and over here is 34. Oh, I should also mention that the other measurement that's required here, besides carbon that I just described, that gives you a concentration. So grams of carbon per kilogram of soil type of thing. We also need bulk density measurements. And so those provide how many grams do we have per unit volume of soil, how many grams of dry soil are in a unit volume of soil. So we take that value and have to multiply it times the concentration of carbon to come up with an estimate of how much carbon is actually there, how much is it sequestered. And that's that mass balance approach that's really critical to looking at whether or not their carbon levels are actually increasing or not. So percentages are part of that story, and we often use percentages of soil organic matter, but that's not the only measure you need if you're going to start to look at how much carbon is actually in the soil itself, which starts to become more influential when you start to talk about carbon credits and other kinds of factors from the standpoint of how management is impacting those stocks, basically, of carbon in the soil itself. So you can see that stocks increased by an average of 8 megagrams per hectare over the course of about 10 years. But there was a lot of differences in field location. Okay, that's the average. You can see that, oh my gosh, the range kind of implies that there's some locations that aren't responding very well, right? And that would come back to some of these eroded knobs here, over here. And those locations probably just don't have, again, the productive capacity to increase that portion of the field to any great extent. And so we're not gaining as rapidly anyway in those locations. Other locations are able to respond, and I suspect those are our higher yielding areas in the field itself. Talking about the field variability, I mentioned, okay, here's some eroded areas, upland positions where you'd expect lower carbon. There's actually some of the lower positions in the field, and some of those on the kind of occur where we've had drainage out of the field itself. That's this little blue line, and this is the low-lying area where the carbon levels are really low there. And I can only imagine that through time and the erosion history, we basically have scoured some of those locations and exported soil, into the road ditch along here in that portion of the field. But you can start to see the complexity of, okay, where should I monitor? Where should I put my georeference location? And how then does that georeference location represent the field itself in terms of what's going on? And I guess where I'm at right now is, well, we should find where the mean is 34. Where's that point? And perhaps that's what we should be looking at least including in terms of our measurement. But it doesn't give a clear indication based on soil or other positions of low-lying areas and higher areas in terms of where you might find carbon. So it's not as clear as you're walking across that field what the stocks might initially be. Okay, so there's the change, and I won't dwell on that, but that's the mean. It ranged from minus 15 to plus 30, so there's parts of this field that are going down, at least according to our measurements. And I will say that there's error associated with our measurements too. We go out with the Gettings probe, we hit here, we try to go back to that georeference location, but boom, it's in a slightly different place. We can't sample the same exact place every time. So it's going to have some noise in terms of our monitoring itself, in terms of what's going on there.
Were you able to correlate the bulk density to this, see how they parallel each other?
Yeah, so the question was were we able to correlate the bulk density with this? And what's going on, at least in that upper 10 centimeters, is that while our carbon concentrations were increasing, our bulk density on the surface is actually going down. So it had to actually compensate, in order to have the stocks that were greater, it actually had to compensate with a lower bulk density. And so as that bulk density goes down, it changes lots of things. It'll start to play with your mind for a while. If the bulk density is going down, that means that actually you may have changed the way a probe, when sampling, actually if you're sampling 10 centimeters, the bulk density has gone down, you actually have more volume there. You've raised the elevation, and so consequently, you're not sampling the same 10 centimeters that you did before. And this is why you actually have to continue that sampling below that in order to get a full profile, and measure the bulk density continuously to actually come up with a stock value. So that complicates it, and it starts to you start to scratch your head from the standpoint of, okay, I can't just sample the top foot. I've got to keep going down. And some people, well, I won't get into, there's all kinds of ways to deal with some of that. Some of it's called equivalent mass. So we're going to go down and just measure the same mass of soil, and that's a different depth, depending on what the bulk density was, and we'll look at the carbon within that. So, but we go down 5 feet, and we think we've probably captured much of the changes, and I'm going to work through each of those depth increments. Here's basically the top foot and that change. And so you could see that a little bit more. We had 8 for the other one, so this is 11, but lots of variability. Again, that range, we tended to see a little bit increase here in some locations, and more for both in terms of the range that we're finding across this field. The patterns look real similar. Some of that's just because these units are not the same in terms of the colors, so don't let that fool you a little bit. So that's the first 11 years, and then there's the changes there that are occurring. We've got some locations here. I could probably go into explaining some of that in terms of our activities. Some of those are just wet locations where we couldn't grow a crop. And so consequently, there was several years in there where those locations were bare, and I suspect that's impacting the carbon inputs, et cetera, in those locations. So here's the subsoil, and this gets back to that question of, okay, what's going on underneath that top foot, which we've actually have quite a few studies on. And in fact, many of the studies that look at soil organic matter have basically targeted that top foot. And we didn't, early on, and many research studies really didn't have the question of, well, what's the stock level? They wanted to know, well, how is management changing that upper foot? Because that has a lot to do with infiltration of water, with turnover of nutrients, et cetera, and less runoff, and those kinds of factors that we were really excited about in terms of changing management to direct seed. We weren't as concerned about what was going on below that top foot in terms of processes. But at Cook Farm we were, and here you can see that, again, oh my gosh, there's a lot of carbon down there, first of all. There's more than what's in that top 30 centimeters in the next 4 feet, okay? Again, that's a lot of feet. You're comparing 1 to 4, but still, if you start to add up that subsoil and the amount of carbon, organic carbon that's there, I've got 10 minutes, thanks. Then we can see that, oh my gosh, there's a lot of carbon here, and in this case, it's trending down overall. So 89 here in 98 and down to 85. So we've lost 4 micrograms per hectare in the subsoil during the same time on average. And there's locations, you can see there's locations that had high amounts of carbon to begin with, sorry, here, and boom, here we are going down. And that comes back to, we've got subsoil carbon there from our history of erosion. Are we maintaining that or not? Remember, with no-till, we start to have more filtration of water, right? So we just changed the decomposition regime. That water used to run off the field, right? So now it's going down in the soil itself. And if we don't capture that with yield, et cetera, and it stays there, it actually starts to augment the decomposition, right? The water, it'll stay wetter for longer into the warming of the spring that Lynn was talking about, and the microbes will start to work on it, and they do. So that's one mechanism of loss in these subsoils that could occur as we go to no-till and have more infiltration, which we want, right? So this is a little bit of a trade-off that we're starting to see here in terms of subsoil carbon. And here's stocks and those changes. It looks uninterpretable, and I won't go in there, but on average, yeah, we're starting to lose some carbon. So now, in 2008, we changed drills. Okay, we were using a Great Plains drill. Many of you are familiar with this double disc drill. It's got a turboculture in front, so there's some disturbance there, but fairly low disturbance. There's drills like cross-slot drill, et cetera, that would provide less disturbance, but basically kind of a low disturbance scenario. And we switched to the horse drill with Anderson openers. They're on 12-inch centers. They have closing discs. So this is still a direct seed, one-pass system, right? But we just upped the whole disturbance factor with the Anderson openers, okay? So these, we're placing fertilizer real nicely at 4 or 5 inches, but there's a lot of stirring. And we quickly saw the duff layer that we built up with the Great Plains basically disappeared within about 4 or 5 years of mixing due to this particular drill's activities. So remember, we're concentrating carbon inputs to this surface. And now we've just provided a disturbance factor at precisely that location where much of our storage has occurred over the previous years. So you can start to imagine, okay, my gosh, that's going to start to accelerate some of the decomposition, the mixing, et cetera, is going to be a more favorable environment for the microbes to work at things. And indeed, that's kind of what we're starting to see. So here's up 10 centimeters, again, that upper location, 34, now we're down to 26. We just lost 8 megagrams per hectare. So that was the carbon we had gained during the previous 10 years. We just lost just switching drills type, still no-till, but still no-till, but still higher disturbance levels with our Horsch-Anderson drill. So that's the stocks changes. I won't go too much into that. I'll recount that, okay, even though that's going down, if we look at this is again 2017, this is 2 years later, we're still seeing organic matter levels that are higher than over here. So what's going on? We could say that over here in our business as usual, we're still losing carbon via soil erosion processes. So everything doesn't remain static. So even though we're different than when we started, and less in that 10 centimeters seemingly, in terms of the 17 years or so of no-till, it's still greater than across the field. And granted, I don't have initial values over here to see if they were the same when all this started, but it seems like the erosion processes have continued, and we continue to lose carbon off of that field over time. So here's stocks 0 to 30. The bad news is that, yeah, we're still losing quite a bit of carbon through that change of drills. At this point, I also brought in the annual above ground carbon inputs. Again, we collect biomass here to see, well, how much carbon is going back in these different sites. And you can see there's a range there. This is the first years that I talked about, and the precip during the 1 to 3 micrograms of carbon per hectare. 0.6 to 3.5, a little bit more of a range here during the subsequent years. The rule of thumb is that we need somewhere around 2 micrograms of carbon per hectare to maintain organic matter levels, but you can see we're kind of above that, but there's locations that are below that. And this comes back to rotation issues that I won't go into. So stocks down in the top 30 centimeters, this is the change. And then stocks in the subsoil, bad news again, they continue to go down at about the same rate. So another 4 basically megagrams per hectare we've lost during the course of time. And so that's kind of the story of stock changes, again, -5 megagrams per hectare. And then if we look at the overall change in the whole 5 feet from 98 to 2008 to 2015, we're going from 156 up to 162 and then down to 143. And so not a good story from the standpoint of particularly high disturbance kinds of direct seed kinds of equipment. I think we're going to basically lose ground in terms of ground gained or potential to gain organic matter, particularly at the surface, because of that high disturbance factor that's mixed with where we're actually putting and placing the residue inputs, the main residue inputs from the crop. Again, I changed that drill up because I was more interested in temperature, and we're colder out here, particularly for our spring wheat, and I wanted to blacken the soil up a little bit with that drill in order to augment we're suboptimal with respect to temperature in the spring in terms of those crops under direct seed scenarios. So, and also we were starting to get a compaction issue below the surface with our low disturbance drill. It's getting up to 1.5, 1.6, and I was starting to get concerned about that high bulk density under the low disturbance type of thing actually impacting our yields as well. So that's why I switched over to the high disturbance drill. So I'm not going to have time a lot to talk about this, but this is kind of emphasizes those carbon stocks, megagrams per hectare with depth, and showing that there's some locations where they're low and high in the sub. So this is all from Cook Farm. And we took points from there and we incubated the soil over 350 days. This is a lot of Alan's work. So this is a way to get the active carbon that's there in long-term incubations. We didn't do it for 5 days. We did it for 350 days. Okay, so this basically collects all the CO2 under laboratory conditions that gets evolved from those soils. And the intent is to see, well, what's the carbon levels like? How much CO2 and what does that look like over time in terms of that respiration? And this is the kind of curve you come up with, lots high respirations to begin with in terms of time here, and over time, then the respiration decreases until it starts to level off by the time you get to 350 days. That's a good time to just stop, right? This is a lot of work. So anyway, that can be used with equations to actually identify carbon that has different, what we call mean residence times. In other words, how long does it stick around? So you can have 5-day carbon, 60-day carbon, and 2-year carbon that we can put into an equation and actually start to look at that in terms of management impacts then on that active fraction again, these 5-day and 60-day kinds of things, versus more recalcitrant kinds of carbon that's just hanging out and not turning over very rapidly. And so some of the results of that just show, here's that mean residence time, here's different layers and depths, and you can see there's a lot, story is there's a lot of this active carbon in some of the cases, down here, sorry, in terms of the C1, that's the 5-day, 60, and 2-year. You can see there's quite a bit of that still in the subsoil as well as the surface. So if their decomposition regime improves, like we did under the laboratory conditions, then it's susceptible then to respiration and loss. And I'll skip over that and this. I wanted to just mention that we have this water extractable organic carbon, and this is basically another laboratory procedure to try to get at that more active fraction. And this is its relationship to some of that 5-day carbon. So these kinds of estimates in terms of incubation studies are not that laboratory friendly. It's not a lot of labs that want to run 5-day or 60 or more day kinds of respiration studies. So we're trying to find simpler methods to relate to that. This is the water extractable organic carbon, and we've also used the permanganate oxidizable carbon, and both of them are related to some of this more active fraction that would be much more easy to identify than these active fractions over time. So I wanted to just finish with saying that there's a lot of issues here in terms of looking at carbon and trying to figure out what's going on with it. This is a cross-section at 5 feet, and notice all the earthworm channels here. This is at 5 feet. Aaron Brooks and others were looking at cores. This is a 10-inch core. There's about 42 holes there. You can see some that are occluded, some have roots growing through them. You notice that every one of them is ringed with dark material, organic matter. So our soils are just becoming more, variable at the surface with the stratification. Also, if you have earthworms present, think about all the organic matter that's actually in these channels the earthworms are creating. And when I go in with a Gettings probe, what am I hitting? So here some of the noise factor comes in terms of me taking a sample, or us, no, not me, my crew taking a sample. And, we get that, but is that sample even representative? Did I hit an earthworm channel or not? Type of thing starts to play or could play into this. And we're getting more of these over time. The earthworms are great architects. They're just distributing everything. I'm done. And here we could have organic carbon coming out of our tiles. We measured that, or here. And we're trying to look at flux towers and organic matter. And of course, we have inputs. So I'm just going to stay there. There are lots of complications here, and it's not an easy thing to follow this type of thing. So thanks, and I'm done.